Sorry, do what?
So I think you can start.
Yeah.
She can just briefly.
Okay, okay.
First topic, Professor Joseph Samuel. He is a professor emeritus at the Astrophysicists and is also a visiting professor at ICTS. He is a theoretical physicist at institutions in several areas, such as conceptual relativity, quantum mechanics, classical mechanics, and we are really honored to have him here. So today's talk will be on space time and disorder.
Yeah, thank you, Ananya, for the introduction and for the invitation to come and talk to all of you. So I enjoy sharing the excitement of research with younger people. And today what I'm trying to do is to get you interested in physics and perhaps give you some of the excitement. And most importantly, I want to give you some of the substance of the subject rather than just the excitement. So this is a picture which is supposed to represent this talk, which has time and dice in the form of disorder. So this is about space and time and disorder. So this is an artist. The artist happens to be my daughter, but that's incidental. Oh, it's not moving forward, is it? I have to point at this. No, it'll be easier if I can do it from here. Yeah, thank you. So now it's working. Yeah. Yeah. Okay. So I'm going to make a connection between two apparently quite disparate things. One of them is a black hole. This is an artist's impression of a black hole. Not a very good one, actually. But you can see that there is a disk around the black hole. And there's a bright spot where material from a neighboring star is falling onto the disk. And when it hits it, there's a lot of energy produced, which is why that looks bright there. And the energy that's released by the black hole is enormous for reasons that we will understand later. And it results in two jets which are shooting out up and down. So that's a black hole. The reason I say it's not a very good image is that it doesn't accurately reflect how a relativistic black hole would really look. It's more like an artist's impression based on very naive ideas. And on the left here, you have a steam engine. A steam engine is something which converts the disordered motion of heat, which is burning in the furnace, into the directed motion of the train. So converting disorder into order is what a steam engine does. So these are the two things which look as if they have nothing in common except the word black, because both are black in color. But I'm going to show you, well, I'm going to convince you, or I'm going to try to convince you, that there are physical principles here as well as here, which have something in common with each other. Okay, this is the rough plan of my talk. I'll have a long introduction of about 15 minutes, spend 10 minutes on relativity, black holes, and this, in some sense, is the most interesting part of the talk, order and disorder, and then some physical ideas that come out of everything which I've said before, and a very brief conclusion. I'd like to thank Ananya, Rohan, Harini, Aditi, and And earlier we used to talk about going around the world in 80 days. And light can go around the Earth in the blink of an eye. Now, this is the common knowledge that light travels at a very high speed. Now, I'm going to contradict myself and say that light actually is going at a very slow speed. And in support of this, I'd like to say it takes 8 minutes to get to the sun, which is a very long time. It takes 10 hours to Pluto, 4.5 years to the nearest star, 3 million years to Andromeda. And there are some galaxies in the sky. When you look at them, you're seeing light that was emitted when dinosaurs were still roaming the planet. So the speed of light is very slow on a cosmic scale, although it's very fast on an everyday scale. And the tension between these two is what we have to get used to and resolve. So the further out you look into space, the deeper into the past you're looking, because light takes such a long time to get to us. So relativity acknowledges the finiteness and the universality of C. That is, the speed of light is the same for everybody, and it's finite. So I'm going to use analogies I told you. Analogies are a way of relating new things to familiar ones. And the analogies are never perfect, but they're almost always useful. It helps you learn something new based on what you already know. Of course, they're used by everybody, poets, doctors, lawyers. I mean, doctors quote president. Just about everybody uses similes and metaphors. And I'm going to use the analogy that sound is very much like light. Both light and sound travel at a finite speed. There are differences because light travels in vacuum, whereas sound travels in air. Both have vibrations at a certain frequency, and the pitch of sound is like the color of light. When you see a thunder flash, I mean a lightning flash followed by thunder, you're seeing both light and sound, and the separation between them tells you how far away the event is. There are many different sources of sound: thunder, voices, horns, and also here is a flute. I'm going to make a sound out of this, if I can. I want you to notice that when I blow onto this hole, I'm generating turbulence, which contains all the frequencies. Only the frequencies that fit here, in some sense, are picked out. And without moving my fingers, I was able to produce two different notes. One corresponds to a note which is lower, and the other one which is higher. And I want to make this point here that everything has a certain natural frequency. Ah, here it is. So I need, perhaps you can come up. Yeah. That's the trouble. That's what you get for standing in the front row, sitting in the front row. Okay. So you just hold it, and we'll face the class. Move a little this side. Yeah. So this is, you just have to hold it. This is one frequency, right, of the slinky. And this is another frequency of the slinky. And like that, there's an infinite tower of frequencies which the slinky has. So this is called the fundamental. And these are overtones. And the same principle applies to the slinky as to the flute. So all waves have this property that if you confine them, as I'm doing here, confining them between the two ends here, they choose out certain frequencies which are natural there. And you can see it in any kind of sound. Even if you fill a water bottle, you can see that there's a sound that keeps going up. Like perhaps even with this second, I don't know. No, I won't try. Okay, but you can sometimes produce a note out of a bottle. The sources of light are lightning, tube lights, the sun, and most importantly, when you disturb an atom, it creates certain frequencies, just like the flute. If I don't blow the flute, nothing happens to it. But if I disturb it by blowing on it, like this, I'm producing a frequency. And the frequency of the set of frequencies produced by an atom is almost like an atomic fingerprint. Each atom has a different frequency. Now, this is one way in which you can see it. This can be done in a chemistry lab. You have a Bunsen burner, and then when you hold, in this case, they're holding a lithium salt, it produces that crimson color. So that is the fingerprint of lithium. Oh, this doesn't play. Okay. It's supposed to play. Okay, it cannot, never mind. Yeah, actually the next one was supposed to be a copper salt, which is a brilliant green and blue color from a copper salt. The point of this was to show that every atom has a particular fingerprint. Yeah, from here also. So, sorry? Okay, 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 fine, fine. Okay, let's go to the next slide. It's okay, it's okay, we'll skip the video. No, no, this is a different one. It's fine, it's fine. No, no, it's in the computer. But it doesn't matter, we'll just go on. Yeah. Okay, so you might have heard that the universe is expanding. And we get signals from distant parts of the universe which are expanding very fast. And rather, the galaxies are moving away from us very fast. What this means is that there is an effect called the Doppler effect, which makes the frequency change when it comes to us. As a result of this, we have a cosmological redshift, and was first detected by Edwin Hubble. And it's not easy to see the Doppler effect with light, though it is possible in the laboratory. But I'll show you a similar effect with sound. So I'm going to make a rather annoying sound using this gizmo. Okay. Can you hear the? Okay, can you hear the Doppler shift? You can hear the sound, the frequency going up and down. Yeah. So that is the Doppler effect with sound. There's a very similar effect with light, which is what we use to find out what is contained in distant galaxies. Now, I told you that c is nature's speed limit. You cannot go faster than light. If you go faster than, galaxies which are moving from us at very high speeds, you can barely see them because of the Doppler shift. So if you disregard the speed limit of nature as being very large, then you end up with Newtonian physics. If you acknowledge the speed limit, you are in Einsteinian physics, and that's what relativity is about. Most of this talk will just stay Newtonian because that's your intuition. You have developed that much intuition. But I will use the fact that the speed of light is actually finite. Atoms emit photons. That is, light actually is not a continuous wave, but comes in discrete packets, which many of you might have learned in school. And these particles of light have energy that is related to the frequency of the light. Can you change the next slide? Okay, these are the two equations I'll use. One is E equal to mc squared. The other one is E is equal to h nu. And this brings up a new constant here. This is called Planck's constant. It tells you about the microscopic world being uncertain. And that's what was related to the dice in the initial slide which I had. So I'm going to use almost no equations except these two. I'm not going to use any equations except these two. And the last century, there were two revolutions. One characterized by this equation, E equal to mc squared. And the other revolution was characterized by this one, that is relativity and quantum mechanics. And to this day, we did not have, just a minute, Bhairav, yeah. To this day, we don't have a harmonious fusion of the two revolutions. So that's why I call it an incomplete revolution. Please go ahead. This is new. This is the frequency of the photon. Yeah. Next slide. Okay, just in case there are any questions. Okay, next slide. Now let me get into the meat of the talk. Relativity and geometry. There's something very similar between the way we think about space-time and the way we think about space in geometry. Okay. Space-time is the set of all events. For example, if you light a cracker at Diwali and it goes off somewhere, that's characterized by location in space and an event in time. So it's impossible to define what we mean by an event precisely, just as it's very hard to define what you mean by a point. But I just take it that you understand what I mean. It's something like a point. Time we normally measure in seconds, and space we measure in meters or centimeters, depending on when you were born. But we can use the speed of light to convert everything into seconds. And this gives a consistent worldview where we measure space and time in the same units, always in seconds or years. So special relativity taught us that we must stop thinking about space and start thinking about space-time. That is space and time together in one, well, combined together. And when we finally get to general relativity, which took Einstein another 15 years or 10 years, he showed that from flat space, you have to move to curved space-time in order to describe gravitation. So the next slide, please. So this special theory of relativity is based on the idea that C is finite and the same for all observers. It changes the view of space and time. You get space and time mixed together to form space-time, and matter and energy are really the same. In this theory, bodies not acted on by any forces move uniformly in straight lines, whereas bodies acted on by forces follow curved lines. And here's a picture that shows that. Here is the collection of all events. This is space-time. Time is plotted like this, CT if you like, and this is space. Now I'm measuring everything in centimeters. That's a straight line. This is a curved line, and this is a piecewise straight line. So somebody who is going without any forces then gets a kick here and a kick there. The next slide, please. In general relativity, we describe curved space-time by a curved space-time, gravity by a curved space-time, and small pieces look like the space-time of special relativity. By putting together small flat tiles, we can produce a curved surface. You might have seen on mosaics, you can produce a curved surface with flat pieces. So bodies follow the local straight lines, but because space-time is curved, they appear to curve. And I want to show you some things about curvature in a very simple way. So given a ball, this is a curved surface. This has got uniform curvature. Every point on this ball is like every other point, roughly speaking, if you ignore the pattern and the dimples on it. But if I want to find out the shortest distance between 2 points, I have to just stretch a string. So that's a straight line. It might look curved to you, but that's actually a straight line on the sphere. And if you take 3 points on the sphere and draw straight lines between them, maybe I'll need a finger, somebody with a finger. Yeah. Everyone has 10 fingers. At least 2 of them you can donate to the noble cause. We'll have this one, and this one, and okay, maybe this one. So this is a triangle on the surface of a sphere. Thanks, I got it, yeah. Oh, yeah, just pull that out. Yeah. Here's a triangle, and if you add up the angles, you'll see that the sum of the angles of a triangle are more than 180 degrees. So this happens with curvature. You couldn't see it? Okay, maybe the 2 of you can do this. And meanwhile, I'll just open the envelopes which are there for you, and you can share the envelopes, and you'll see 2 sheets in it. Yeah, you'll see 2 sheets of paper and some rubber bands. Leave the rubber bands alone. Just take out the 2 sheets. So one of them looks incomplete like this. And then when you put the 2 lines together by like this, the other one, the incomplete one, when you put the 2 lines together, you'll find that you have a triangle where each of the angles is 90 degrees. This is something you don't see in flat space. And then if you take the other sheet of paper and put the 2 O's together, you'll find that between the 2, there's a polygon with just 2 points, 2 vertices, A and B. There are two straight lines joining those lines. So between 2 points A and B, we've got more than one straight line. So this is as what I would call a biangle instead of a triangle. So you get biangles in curved space, which you don't get in flat space. Okay, the next slide. So this is an artist's impression of a curved space-time. This is supposed to represent a black hole, where it's curving so badly that it goes down. Yeah, this one, you just put the two O's together, like that. It's like an ice cream cone, except that the cone angle was different in the two cases. So the next time you eat ice cream, remember, you're dealing with a curved space. Okay, the next slide, please. So why did Einstein propose this idea? The idea was proposed because he realized at some point that acceleration and gravity are the same thing. Gravity can be eliminated by yielding to it. For example, if you drop two objects, all these are too precious to drop. But if I drop two pieces of chalk, yeah, here are two pieces of chalk, and I'm going to drop them, and you'll see that you'll hear only one click when it falls on the table. They fall together. So that's because in a gravitational field, all bodies fall exactly the same way. Yeah? So this is the basic idea that Einstein had when, well, after thinking about it for many years, and he realized that you can eliminate gravity. So gravity is not really a force because you can eliminate it. It's a bit like the centrifugal force, which you can eliminate by going to a different frame of reference. Now, let me see. Yeah, from this, he concluded that since all bodies fall the same way in a space-time, the lines they follow in space-time as geometrical curves are the same. So you can think of those curves as being a property of the space-time rather than of the body which is falling. Yeah, and he decided that he postulated that those lines are really the actual straight lines. Because if you go to a small patch, each piece will look like a straight line. So when you put a lot of local straight lines together, you get a global line, straight line, which you might think it's curved. When you see the planets going around the sun, you might think that that is actually a curved line, but it's not. It's really a straight line in each small patch. The next slide. So I don't know if this will come out. The video may not play. Let me try. That's, yeah, it's sort of the aspect ratio. Okay, let me explain what I want you to see here. When the bottle drops, the bottle has got two holes drilled in it. And if I hold the bottle like this, the water will leak out. You'll see two arcs here. But when I drop it, when I yield to gravity, the bottle falls and the water will not come out. So gravity is ineffective in that frame. Just try to play it. See, it stopped now. The water is not coming out at all. Yeah, and the next one. So that shows that there's no gravity in a freely falling frame. Okay, the next one, this is a different one. We are dropping it, and when it hits the ground, you'll see a spurt coming out to the right. Never mind the spurt that's going up. Yeah, you saw something coming from the bottom. That's because there was a lot of deceleration when it hit the ground. So the deceleration can simulate a gravitational force as well. So I'm so glad this video's worked. Thanks. No, it's okay. I think we'll go on for the time. I want to finish. Yeah. So, yeah. So I need the Mathematica file. Yeah. So I just run this. Yeah. So I'll keep this playing. I'll tell you how this engine works. This is a perpetual motion machine. So what you have here is, what is this? What is it? Yeah, this is a perpetual motion machine, which we know is impossible, but I'm going to describe it. So here I have a set of atoms which are in excited states. They have atoms which have been put in excited states. And the blue ones are atoms which have not been put in excited state, which are in the ground state. Now, these have got slightly more energy than those, and therefore they have slightly more mass. If you have slightly more mass, you're going to fall. This is going to turn because there's more. The left side here is heavier than the right side, and this is going to fall down. And it's going to keep rotating. In fact, it's going to keep accelerating. I've drawn it as going slowly because of some friction or something like that. But this is a machine that will go on forever. But you'll say, what happens when I go to the top here? The heavy part will come here, and the light part will go to the other side. But what I'll do is when it gets to the bottom, I'll take a laser beam and de-excite the atom and send it up by mirrors here and re-excite the atom over there. Yeah. The net effect is that the red atoms are always on the left and they're heavier. The blue atoms are always on the right and they're lighter. And this will keep going on forever. So can someone tell me what's wrong? What? Yeah, but I can use the laser to just put enough energy here to get it over here and send it up there. That's true, yeah. But suppose I tickle the atom with a laser, make it de-excite, I'll get 2 photons, right? And I can send one up and keep the other, I get my photon back. There's a process called stimulated emission in which you can send a photon and make an atom come down, and you get 2 photons out. So you get your photon back, and at the same time, you de-excite this atom, and then you send the light up there to excite the atom on top. So if this were true, then we have solved the world's energy problem, because we can keep generating energy from such a machine. Obviously, it's not true. And the resolution is that when I send the photon from here to there, it loses energy. Yeah? Huh? This is called the gravitational redshift. So if you have two people, one deep in a well and one outside, the guy in the well, his light, when it comes up to you, it'll be slightly redshifted. It's a very small effect, but this is the gravitational redshift. Yeah. Or if you have 2 orchestras, one playing outside the well, one playing inside the well, the guys who are inside will play at a certain rate, but these people have to play at a different rate. They have to play faster. I mean, they have to play slower if they're upstairs. Yeah. Okay. So this convinces you that there is something like a gravitational Doppler shift. I mean, gravitational redshift. Now, all clocks are based upon atomic clocks, usually these days. Yeah. So if you have atoms down here and up there, they will be ticking at slightly different rates. Now, that brings us to the next point. Let's go back to the other slide. Yeah. So 1 second at this height is the same as slightly more than 1 second at that height. Yeah? And this is the path of a light ray. Time is being measured like this, and height is being measured like that. This is the path of a light ray, and that's another path of a light ray at a later time. This should have been a parallelogram, but you see the opposite sides have different sizes. This can never happen in flat space. In fact, this is space-time. But this is proof that in a gravitational field, you have curved space-time. Because the usual rules of geometry are breaking down. Parallelograms don't have equal sides. The next slide, please. Yeah, this is a good point to stop for questions. Lots. Yeah. Yeah. Yeah, that's right. Yes, exactly. Yeah. Yeah, gravity is not a force in a small part which you can regard as flat. But when you put the different flat things together, you can feel the effects of gravity by some difference in the way gravity acts. So one example of this is the tides. If you go to the sea, you see that the water sometimes comes up high and goes down low. That's because the gravitational field of the moon locally on Earth acts differently at different points. I can come back to this question at the end if I have time. So gravity is a real force, but it's not the force that we are looking at now in the small part. Yeah. Okay, the next slide, please. Now, black holes are generally thought of as traps of light. Yeah. So black holes are things which trap light and keep it trapped. They don't let light escape. And to understand this, you start with the notion of an escape velocity. Given any body, it takes some certain energy to put a spacecraft into space. Like you have to give, suppose you don't have a spacecraft, but you want to throw a stone. If you throw it up, like suppose I throw this up, it'll go up to that height and come back down. I keep throwing it high with more and more energy. At some point, the energy will be so large that it'll escape from the Earth's orbit. That notion is called the escape velocity. And it doesn't matter whether you throw it this way or that way, horizontally. It should be called the escape speed, actually, because it's not a velocity, but a speed. So the escape velocity is the general term, so I'll continue to use that misnomer. The escape velocity of a body depends on its mass and its radius. If the mass is so high and the radius so small, it can happen that the escape velocity is equal to the speed of light. Then we say that it forms a black hole. This is a Newtonian argument, first given by Mitchell, is a clergyman in England, Laplace, a very distinguished astronomer in France. And finally, in this century, Schwarzschild came up with a solution of Einstein's equations that actually describes a black hole, which was not appreciated earlier. And the work of the Indian origin astrophysicist Chandrasekhar in the 1930s showed you that they are real astronomical things which do appear in the sky. So stars shine because they're compressed by gravity, and the pressure causes nuclear reactions and causes them to shine. But when the nuclear fuel runs out, the pressure which holds them up is no longer available, and they collapse and get smaller and smaller and smaller. But when they get really small, it's quantum mechanical effects, that is to say the uncertainty principle, that causes some motion of the electrons that resists the pressure of gravity. But when the star gets even heavier than that, it cannot resist gravity and it collapses to form a black hole. This is the work of Chandrasekhar in 1930s, which was very controversial at the time, but it's absolutely right. The next slide. I told you that black holes are sources of energy, and it's really true. Well, I told you that black holes are at light traps, but it's very easy to see that they're also sources of energy by simply reversing the earlier argument. The quasars that were discovered in the 1950s are showing an enormous amount of energy coming out from a small region, 1,000 times the luminosity of our galaxy from a system which is no bigger than our solar system. That is one light day. So to understand why they're so good source of energy, what you have to do is to reverse the argument of escape velocity. I told you that in order to escape from a black hole, you need a hell of a lot of energy. But then if you fall into a black hole, you'll release the same amount of energy from energy conservation. And so all that energy will come out if you can tap it out of there. Either if it falls in completely, you get no energy. But if you manage to take the kinetic energy at that point and convert it into light, you can send it out from outside the black hole. So the next Mathematica. See. Yeah. Right. So I'm just going to run it. Yeah. So I'm going to make a few more annoying noises. So one of them is, I'm going to use the Mathematica file to produce a fixed frequency. And I'll pretend that from infinity, I've dropped somebody into a black hole, or rather an emitter of sound. Although there's no air, let's put in an emitter of light and then just convert it into sound, just to think about it. So the first thing is a uniform constant frequency, which is what I'll hear if I'm not thrown into a black hole. It's just a fixed frequency. Yeah. Now, when this same object is thrown into a black hole, the one that's emitting this sound, there are two effects. One is the gravitational redshift coming out of the hole. The other one is the Doppler shift, because he's got a velocity moving away from me. So you'll find that the same waveform, which was a constant in the first experiment, now becomes something like this. That's the sound of someone falling into a black hole. If he was yelling at a fixed pitch, then that's what you would hear. I'll just play it once more. Okay. So back to the slides. Okay, now then, that's right. The next slide. So as sources of energy, the astrophysical sources are not that efficient. Here's a better way to, if we find a black hole, this is one way to save the planet. Okay? If we find a black hole somewhere around, we can leave the black hole here, and from the Earth, we take all the garbage that we produce, all the junk, right? And we lower it slowly into a black hole using a pulley system and use it to lift weights on the planet. And we can extract energy, and then when this weight and the garbage reaches the close to the black hole, you just let it go. And then you've acquired all this energy on Earth. You can use it to pump water upstairs. And you don't have any problem with generating energy. There's nothing wrong with this as a perpetual motion machine if you have a black hole. The trouble is we have to find a black hole. I mean, we can find them, but they're very far away. In practice, the efficiency in astrophysical terms is only about 5%, but the conceptual idea is the same as what I'm talking about here, to extract energy from a black hole. And it was just realized in the 60s that the universe is a very violent place. There are energetic events involving black holes, and that led to the birth of relativistic astrophysics, which is a very burgeoning field these days, and relativistic cosmology. And if you have any inclination towards science and mathematics, this is one of the places that you should think about going to. Yeah. From the outside, it looks like the black hole is completely, it's a static object. And when you look from the outside, it's just a place where things can disappear into. It can go in there, you'll never see it again. If you commit a crime, take all the evidence, throw it into a black hole. Nobody will catch you. Okay. Better don't commit a crime. And suppose you fall into a black hole, you get an entirely different view. Yeah. You want to commit a crime, is it? Okay. Yeah. Yeah. Yeah, but it'll get more and more redshifted, right? It'll be harder and harder to see. No, see, the thing is that when it falls into the black hole, the photons that come out come slower and slower and slower. Come out, it takes them a longer and longer time, no? So suppose you throw something into a solar mass black hole, within a few milliseconds, nobody will be able to catch you. I mean, okay. That's true. You can also throw it into a solar mass star here, but this is better. Okay. And you might have seen, yeah, if you get into a black hole, what you see is something which is not static. You find that things are changing with time, and when you fall in, there are tidal forces that will rip you apart. That is the two. I talked about tidal forces earlier, the moon's tidal force on the Earth. Your two arms will be pulled apart, pulled together, and it depends on how you're falling in, your head and your legs will be pulled with different gravitational fields, and you'll be stretched. It's very painful. At some point, your body will be torn to pieces, to atoms, and after that, each atom will be torn to shreds. And let's not get into that. But this, in some sense, is the edge of space-time. And that's what is called a singularity in physics. This is a little bit like the edge of the Earth. The Vikings were very afraid of falling off the edge of the Earth. They thought they would sail into the sunset, and at some point there would be the edge of the Earth. Beyond that, there would be dragons and all that. No? So it's a bit like that. We don't know what is there in the singularity. It's one of the great open problems of this subject. And another thing that comes out from this is that if you hang around near a black hole, you age differently from when you're outside. So if there are two twins, one stays out, the other goes near a black hole and comes back. As you saw in the movie Interstellar, A guy is able to be present at his daughter's deathbed because he has spent a lot of time wandering around in black holes, near black holes. Okay, the next slide. So this is from the movie Interstellar, and it's actually a more accurate representation of a black hole in the sense that there's a disk surrounding the black hole, but these parts here are on the other side, and when light comes over the black hole, the gravitational field of the black hole bends it, and it makes you look like this rather than flat, as I saw earlier. Similarly, thing happens below also. You're looking at it sort of edge on. And the ring here is a set of light rays that are trapped forever, going round and round the black hole, and some of them are escaping and coming to us. These are marginally trapped. I mean, just about to be the next one. Now, this is a picture of a black hole that was made a long time before Interstellar, and this is from theoretical calculation using computers of the 1970s. This also shows you that there's a disk which is rotating around the black hole here, and here you find that it's very bright because the material is coming towards you. It looks brighter when it's coming towards you because of the Doppler shift. Okay, now we come to the most interesting part of this talk. This has to do with heat engines. I need a drink before I can do that. Yeah. Mm-mm. Sorry, what is that? They didn't use it. Huh. Oh, okay, okay. I'm sorry? Yeah, yeah. Can we get the answer? Okay, now I want to pose a question. Um, Environmentalists tell you to conserve energy. That is, you switch off your lights and you generally be very economical with energy. Don't turn on the AC and, things like that they tell you. But physicists tell you that energy is conserved. So why do you need to conserve energy if energy is anyway conserved? That's the question. Yeah, very good. Yeah, absolutely. So that's the answer to this question. Actually, this question was asked to me by about a sixth standard girl who came from Kerala to our institute when I was in the Raman Institute. So it's a very genuine question, and that's the answer exactly. That there are two kinds of energy: ordered energy and disordered energy. So light that comes out of here is ordered energy, and when it hits the walls, it creates a bit of heat and molecular motion, and those molecules are vibrating in any which way, and that's disordered energy. So you can waste energy by converting it from an ordered form into a disordered form. Yeah, next slide. So heat is a degraded form of energy. So total energy is conserved. That involves ordered energy plus disordered energy. And disordered energy is heat. So you can convert electrical energy to light, as we're seeing now. Um, yeah, I just a few more minutes. Yeah, yeah, yeah. Let it be on. Let it be on. And you can convert kinetic energy to potential energy like this by throwing up a chalk. What is kinetic here becomes potential there when it goes up there. And you can convert potential back to kinetic, right? When it comes back. So it's freely convertible from one kind of energy to the other. All sorts of energy except for heat. Heat is the worst kind of energy. So energy is a bit like money. Money is generally conserved, but you can waste money, right? You can buy something that nobody else wants to use, and that's a waste of your money. It's a bit like that. You can buy a useless, treadmill machine and keep it in your house, not use it. That's a waste of money. In the same way, you can take energy and either use it constructively or simply waste it. So the first law of thermodynamics, which tells you that energy is conserved. The second law of thermodynamics tells you that you can waste energy. That is, there's a limit to how much you can take disordered energy and convert it into ordered energy. Sorry, what's that? Yeah. Let's see. Yeah, go ahead. Next slide. So the entropy is a measure of disorder, and yeah, the general idea is that the second law tells you that entropy always increases. In other words, that if you do nothing, the entropy of the planet will keep increasing. Yeah? Well, of a closed system will keep increasing. And when you have a fridge, for example, you think that the fridge is cooling the inside. It's true, it's cooling the inside, but it's also heating the outside. And in order to do that, it has to take energy from the outside. And if you switch off the energy source, the fridge will get warmer and warmer and reach the same temperature as the rest of the room. So it might be counterintuitive why there's a connection between entropy and heat. And for this, I'd like you to take up the rubber bands which are in the envelope. And take a rubber band. There are many of them. You can just pass them around. Take a rubber band and put it on your forehead. Okay? And if you pull it suddenly, your forehead will feel hot. If you pull it suddenly, don't hurt yourself. Just pull it like this, rapidly like that. Can you feel the heat on your forehead? You have to do it fast. And when you let it go, it feels cold again. So in fact, this can be used as a refrigerator. I could go to a hot body and then take the heat from there and put it into a cold body. This could be, or the other way around. Could take it from a cold body to a hot body. This can be used as a working fluid for a refrigerator. So the intuitive connection between disorder and heat comes about in the following way. When I pull it, all the molecules are pointing in the same direction. Rubber is a polymer. It has got so long molecules can be in any which way like that. There are a lot of configurations where the molecules are disordered, but there's only one configuration where the molecule is straight. So when I pull it, I'm taking all the rubber molecules and making them straight. There's only one such configuration. So there's very little entropy. When I let it go like this, there's a lot of entropy. So everyone convinced? Did you try it? Okay, okay. Yeah, okay. Not quite level, so I'll just try to level it with this. Yeah. Or should I level the table? This is slightly sloping like that. I'll raise the table at this point. Or maybe this is easier. Yeah. I think it's flat now. And so R&D will press this down. Yeah, from both sides. Yeah. Put both your hands on it like that. Yeah. And keep it pressed down for a while. Yeah. Just let the thing. Okay. Fine. So can we go to the next slide? Okay, this is an example of order and disorder, which I got from yesterday's discussion. And the hand over there belongs to Aditi. Yeah, that same hand that she raised. No, the other hand. Okay. So she was trying to disentangle a slinky, which they had kindly bought for me because I couldn't bring mine along. So you can see this part, it's a very neat helix, neatly ordered. When you get up there, it's a horrible tangle. That is a disordered configuration, and this is an ordered configuration. There's only one configuration like this which is well ordered, or very few configurations which are ordered. Up there are a lot of configurations which are a mess. Yeah. So it's easy for things to go out of, get muddled up and disordered. So if you lend a slinky to your friend, you can be sure it'll come up tangled up. That's what happened to these people. We don't have to mention the name of the friend. Okay, so this is a device which, we'll wait some more time, which does not have a battery in it. But it's a device that works between two temperatures. One of them is the temperature of the ice, which is in the plate there. The other is, is Harini's body temperature. That's a heat engine. So she's the hotter body and the ice is the colder body. And by transferring heat between the hotter body and the colder body, we're actually able to generate directed motion. Yeah. Yeah, a little bit, but your blood supply will keep it. Yeah, it's getting there. Slowly it'll get there. I think it's working. Okay, let's go to the next slide. So if you have a closed system, that's got a fixed total amount of energy. If you do nothing, all the energy will tend to dissipate into heat. The final state will just maximize the disorder or the entropy for a given energy. This is what we call a thermal state. And that's the notion of temperature. So we cannot extract work from something which is in a thermal state, but we can extract work from if there are two different temperatures, you can extract work. And that's what I'm showing you with this heat engine here. Yeah, it's working. Yeah. So she's doing nothing apart from, I mean, she's not putting any work apart from just holding it like this. And because of the heat engine running between these two, you're getting directed motion from what is molecular motion. This is an example of a heat engine. Now I'll show you a slightly more dramatic example. Wait, I'll skip that one. We'll go to the next slide. Okay, I'll come to this later. I'll show you one more demo now. For this, I need a cup, which is again kindly presented to me by Ananya. That will do now. Thanks. Yeah. So this was working. What will happen if I replace the ice with something hot? What? It'll also work. Okay. But any difference between this? What's that? It'll go anti-clockwise. Okay, let's try that and see. So first, I think it'll stop because now the bottom will get hotter and hotter. Okay, so it did stop. Let's wait a little while. And it was going this way, right? Yeah. So let's see. We'll give it some time to get hotter. So I'm running out of time, am I? Yeah. Actually, that has to do with the way this thing is set up. The direction of motion has to do with the hardware. Yes. Now the general intuition is it will go the other way around. Let's wait and see if it happens. Okay, we'll come back to this. So closed systems, okay, I can go to the next slide now. So I've not yet made the connection between black holes Yeah, not yet made the connection between black holes and temperature and entropy, things like that. So the reason I can do that is that if I have a black hole, I can throw disorder into it. I can take the garbage I was talking about. Garbage generated from any house is a source of lots of entropy, and just throw it into a black hole. I've reduced the entropy of the outside of the black hole. So I can decrease the disorder in the universe if I have a black hole, right? That was the basis of the garbage scam for generating energy to run the planet. Now, this would violate the second law of thermodynamics. Except that if the black hole is part of the universe, I could say that the black hole also has entropy, right? Because when I throw the entropy into a black hole, maybe the entropy of the universe decreases, but that of the black hole increases. But now I come to an amazing conclusion. I think it's actually accelerating. Yeah. And you can also see if I try to set it the other way, it will not work. It stops very fast. Okay. If I throw entropy into a black hole, it will decrease the entropy of the universe unless I admit that the black hole has geometry, has entropy. Now that is an interesting conclusion that became clear only in the 1970s. The entropy of a black hole is something geometric. We're talking about geometry of space-time quite a lot, and it has to do with the area of the black hole. It has been shown that the total area of black holes always increases. That is, if I throw something into a black hole, the mass of the black hole will either stay the same or increase, depending on how much matter I throw in and how I throw it in. So the black hole will always grow with time, and the area will always increase. And if I have two black holes merging into one, the total area has been shown to be more than the initial area. So the area of black holes also obeys the law very much like the laws of thermodynamics. Yeah, if you extract all the energy, I was telling you, if you take out all the energy, then the mass of the black hole does not increase very much because you've taken the energy out. But if you just throw it in from infinity, it's an irreversible process and the entropy increases. Yeah. Yeah. Yes. No, no, no. Mass is for the black hole, mass is proportional to the radius. And then you get radius squared, which is dimensions of area. Good question. Yeah. Yeah. So actually, that comes out if you look at the formula for the event horizon of a black hole, the Schwarzschild formula. It tells you the radius of the black hole is given by 2gm upon c squared. In gravitation and thermodynamics, and this is the subject of current research. And many people all over the world, including Amitabh here, are working on topics like this. So let's go to the last slide, which is my conclusion, I think. So what I've shown you is that black holes are macroscopic objects with a microscopic description. That is, we can talk about this whole black hole within the theory of general relativity, where we don't have to put in a lot of complexity. It's a very simple object from a certain point of view. So current research deals with these questions. If I throw information into a black hole, is it really lost? And this goes to your question. There are people who agree with you that black information is not lost in black holes, that you can get it in the Hawking radiation. Okay. Oh, okay. Okay, anyway, they agree with you whether you agree with them or not. That's true. It'll hang around at the surface, right? But it'll emit a finite number of photons before you don't see it anymore. That's another effect, no? It's a quantum effect also. Okay, maybe we can discuss later in Bangalore, no? Okay, now, there is a conflict between this idea that black holes carry entropy and the notion that, what are the degrees of freedom that carry the entropy? What are the degrees of freedom responsible for black hole entropy? Are they stuck at the boundary, as some people believe? Or is there new physics beyond GR? There certainly is, I think. And this new physics is probably something like quantum gravity. That's a subject of very intense theoretical activity because experiments are hard. And let me just close by saying that science is a combination of imagination and skepticism. You have to imagine absolutely crazy things in order to do science, but you should also be skeptical of extremely crazy things. It's that combination of being imaginative and skeptical that causes good science to come out. It's not enough to just imagine wild ideas and believe in them, or believe in them because somebody from Princeton or somewhere else says so. It's also important to question it from your own point of view. And if you generate enough skepticism, the tension between imagination and skepticism will create new physics. So I'll stop here. Yeah. Yes, yes, right. Yes, yes. In fact, that description is done for all. For example, if you take a black body radiation in a box, you can do exactly what you're saying. You can characterize the disorder from a mathematical point of view. Hmm? When it comes to black holes, we don't know where the degrees of freedom of a black hole are. Yeah, 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 yeah. It looks like it's an inert object, you know. Yeah, yeah. Yes, right. Yeah, yeah, right. That's right. Yeah, correct. Yeah. I like questions from the younger people, especially because I think you must be having points which were not, there must have been points which were not clear in the talk. You know. If not, we can wind up. Uh, I think, Anati. No, no, please. Yeah, yeah. You talked about that using curve geometry. Hmm? So the sun, like I showed you that picture of curved spacetime, the sun distorts the spacetime around it in such a way that going around the sun is the shortest path for the planet. So it's a different description of gravitation. It's absolutely successful. It's more successful than Newton's theory. If you take the limit of slow velocities, you end up with the same laws that Newton had of the way the planets move around the sun. But if you look at the innermost planet like Mercury, the speeds there are higher, it's mildly relativistic. And then you find that there is an effect called the precession of Mercury. The orbit of Mercury keeps changing like that. And that has been seen hundreds of years ago. They couldn't explain it within Newtonian gravity, and Einstein's gravity exactly explained it. No, no, that's true even in Newtonian gravity. Any object which has angular momentum cannot fall into the sun because angular momentum is conserved in a spherically symmetric situation. So it goes round and round like this, right? But if you have an elliptical orbit, hmm, according to Newton, the elliptical orbit is closed. After 1 year of the Earth, let's say, it comes back to the same point. So according to Einstein, that major axis of the ellipse will shift by a small amount. It's only 42 arc seconds per century. It's a tiny amount, but astronomers measure things like that. It's a huge distance in this in action terms. Yeah, yeah, acting upwards. Yes. Uh, no, if you sit in a car, hmm, if the car is going around a bend, you feel that gravity is pulling you to the left, right? If your car is turning to the right, hmm, that's the simulation of gravity by acceleration. Hmm? That's right. So right now we're talking Newtonian. Forget about Einstein's thing. So all I'm saying is that if you're in an accelerated frame of reference, you think there's a. If you go to a lift and you put a weighing machine on the floor, and you press the button and stand on the weighing machine, you'll find that the weight increases. So the gravitational force of the Earth is being increased when you're going up and decreased when you come to a stop at the Earth. Yeah, Einstein's basic idea is that the two are indistinguishable. There's no difference between them. So he called it the principle of equivalence of acceleration. Yeah. No, no. The other forces, like electromagnetism, they depend on the charge. If I take a neutral object in an electric field, it's not affected at all. Yeah, yeah. See, forces can be accelerated due to gravitation or other forces as well. So the gravitational forces, according to Einstein, don't exist. You can remove them by just falling with them. Hmm? That's right. That's right. Yeah. Yeah. It works the other way. You can simulate gravity with acceleration. You can eliminate gravity by acceleration. Okay. Yeah. Yeah. Einstein was, well, he was talking about the equivalence of the two. Hmm. Yes. Right here. Yeah. 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 Right. Yeah. Okay. Thank you all for your attention. It's been a pleasure interacting with all of you and with all of you as well. Yeah.
Thank you, sir, for the